Hi, I'm Miss Vu. Let's have a look at the derivative today. Previously, we've seen the average rate of change and instantaneous rate of change. If you haven't seen those videos, please watch them first so that this video will make a little bit more sense. So the average rate of change, we previously said that it's the gradient between 2 points, and it gave us the average gradient between those 2 points. And we did that by drawing what we call a secant. And we said for any function y equals f of x, the average rate of change of y with respect to x over the interval a, b is the gradient of the line through a, f of a, and b, f of b. So the x value, the y value, the x value, the y value. So we did the same thing as what we used to do when we found the gradient of a straight line, which is finding the difference in y over the difference in x, y2 minus y1, x2 minus x1. So that's how we found the average rate of change between 2 points. Now if we wanted to find a gradient for that point, this wasn't very good because it gave us the average between 2 points. Then we went and had a look at instantaneous rate of change, which is the black line over here, where we drew a tangent instead of a secant, a tangent to find a gradient at that point. But with the tangent, even though we found the gradient at that point, you and I got different answers because I could draw something like that, but your one might be a little bit to the left or to the right, and even though it's a little bit more accurate than two very far apart points, it wasn't exactly the same value. So how can we make the secant, which was really different to the gradient at that point, become more like the tangent or more accurate like the instantaneous rate of change? So how can we combine these two things? So that was good because we had a formula between 2 points, but the gradient was nowhere near that point. That tangent was good because we drew a gradient that looked like that point, but it was inaccurate because of the way we drew it. So how can we make this secant become more like the tangent? So use the accuracy of the secant with the accuracy of the tangent to find a gradient at that point. How do we do that? So let's have a look at this point here. Let's say I wanted to find the gradient at that point where the x value is x and the y value is f of x. Now, if I use the secant, the average rate of change method, I'll pick another point. Let's say from here to here, there's a distance of h. Then the other point, what would it be called? So if this is 3, h is 4, then 3 plus 4 would be 7. I'll be 7 there, right? So if this is x, this is h, then that point would be x plus h. If that point is x plus h, where h is a little number, then the y value would be f of that. So f of x plus h. So I hope you're following. So this is, I picked any x value, could be 5, could be 10, could be 12. Then I'm adding a value to go to the right on the x-axis. So if this is 5, I add maybe h is 2, then that is 7, then that will be f of 7. So I'm just using numerals here. Try to follow along. So x, and then x plus h to represent a value to the right of it, and the y value will be x of x plus h. So if I had this, then the gradient would be between the average rate of change. I know how to do that. It will be that take away that over that take away that. But that's not very accurate. So how can we make it more like the tangent? We could make h smaller and smaller. The smaller we make h, see, the smaller we make h, the more we can see that it becomes closer to the tangent. Oops, hang on, let me show you. See, the blue line is between the two faraway dots, and then as we get to the darker line, see the darker line, it becomes closer to the tangent. So as we can see that as h becomes smaller and smaller, so the two dots are coming closer and closer, our secant becomes pretty much like the tangent, or our line between the 2 points become more and more like the line between that one dot instantaneous rate of change. So what we want to do is find the 2 dots where h is so small, and we have done a little bit of maths talking about when a number becomes really close to a number, but not that number, and that was limits. So when h becomes so small that our line becomes pretty much between the two dots that are so close together that it looks like the tangent, then we have found the gradient at that point. So let me recap. The gradient between 2 points, very inaccurate for that particular point, but if we make the 2 points closer together, then we can see the blue lines becoming the black line. The blue line, which is the gradient between those 2 points, become closer to the gradient at x. So it becomes closer to the tangent. So when we have h really small, then see this h distance becomes, instead of having 10 for h, we had 1 for h, or 0.1 for h, or 0.001 for h. Then the two dots will be so close together that we pretty much drew a tangent. So it would describe the number becoming, h becoming a certain number as a limit. So how do we get to this formula? So the gradient is y minus y1, so f of x plus h minus f of x, over the difference in x, so x plus h minus x. But we can see that x minus x will cancel out. Let me recap before we get confused. This is just the average rate of change, so y2 minus y1 over x2 minus x1, and it looks like that. Now we simplify, and we notice that when we go x minus x, we end up with just h. So we have this average rate of change, but we want h to be really small so that we have pretty much calculated the gradient at that point, because h is so tiny. But when we do that, we can't let h be equal to 0, because if that's 0, then something over 0 doesn't work. But we can get really close to 0 to figure out what it is. We also have a symbol to represent all this, so the gradient or the derivative, and it's f dash x. So that dash means the gradient of f of x. So here we have the formula, and we call it derivative. And we refer to this particular form of derivative because we're going to look at other derivatives later on. This particular format is called differentiation by first principles. It's easy to remember because this is the first time we're using a formula to find a gradient at a particular point. So this is the most accurate thing we've done so far. Differentiation by first principles. If the equation is f of x, then you would use the symbol f dash x. But if the question had y and x, then you would write dy over dx. dy over dx comes from delta y over delta x, where delta means difference. It's a Greek letter, but we're meaning in mathematics difference of y over difference of x. Difference of y over difference of x. y2 minus y1 over x2 minus x1. So difference of y over difference of x. So what we call this is derivative. This method is differentiation by first principles. If you see f of x, then the derivative is f dash x. If you see y, the derivative is dy dx. Let's do a few examples. It'll get a little bit easier when you see it. So example 1, find the derivative of each of y equals x squared plus 3 using first principles. Example 1, find the derivative of y equals x squared plus 3 using first principles. So let's write out our first principle formula. Because we're doing y, we're going to write it as dy dx instead of f dash x. So the limit of h approaching 0 of fx plus h minus f of x over h. So how do we do this? So we're going to substitute f of the x with x plus h for this. And then for f of x, we're just going to write it out. So let's write that out. So we can see that f of x plus h is, so wherever you see x squared, you're going to put x plus h squared, then plus 3. So that is that section. And then f of x is just rewriting that over there. But I'm using brackets because there's a minus there, and I might muck up the minus with the 3 if we forget to do so. What can you do now? Always do what you can. So when you look at that, what can you do? You can expand. So let's expand. So once we expand, we have x squared plus 2xh plus h squared plus 3 minus, now we get rid of the brackets, x squared minus 3. See that minus 3 is a very common recurring mistakes when I mark tests, so make sure you use brackets or be super careful. Now what can we do? We look at it and we're a little bit scared because there's so many things, but what can you do? You can always cross out things that cross out the same terms. So x squared and minus x squared cancel out, and then can you cancel anything else? This is 3, and then we're left with this chunk 2xh plus h squared over h. Now what can we do? We can take out h and cancel it out. So now we have h, 2x plus h. Now this is a factor, this is a factor, I can cancel that out. Remember, you can't cancel that h because that's part of this factor, so you need to cancel factors. So now we have the limit of h approaching 0, 2x plus h. Remember how to solve limits? When you plug in the value, then you can get rid of the word limit. So let's plug in the value 0 for h, and now we have 2x plus 0, which is just 2x. So the derivative of y equals x squared plus 3 is 2x. Oops, there's that working out line there, ignore it. It looks like a lot of working out, but it isn't much in between here. All you have to do is remember, substitute x plus h into the equation, that chunk, minus f of x, use bracket, over h, and then work out the limit once you have simplified it. So substitute x plus h minus x over h, simplify, and then sub in the limit and find your derivative. Let's do one more. Example 2. Find the derivative of f of x equals x cubed plus 5x minus 4 using first principles. So again, let's write the formula, and this time I'm writing f dash x because we're doing f of x instead of the dy dx. So now we plug in x plus h for that minus the x for that. So the x plus h into where x is, we have x plus h cubed plus 5 x plus h minus 4, then minus that chunk. Pretty much copy paste it. Use the bracket so you don't stuff up your minus. Now we expand. Do you remember how to expand cubic? So it was 1 3 3 1 pattern where, and then x goes from cube to 1 and h goes from none to cube. So let's expand that. So x cubed plus 3x squared h plus 3xh squared plus h cubed. So remember, the pronumeral for each of these terms is 1 3 3 1, and the power of x is cube squared 1 none, and the power of h is none h 2 cube. Okay, that's just that part there. Now plus 5x plus 5h minus 4, that part is easy, and now we're just expanding the negative, so that's negative, negative, and positive over h. And notice that I'm always writing the limit until I evaluate the limit, so make sure you don't miss that in your working out. I know it's a bit tedious because there's so much writing, but just be patient and you'll get to the answer quite accurately. So now we cancel things that are the same, all the same terms. So minus 4 and the 4, anything else? The 5x and the 5x, and then that's it. So now we're left with that, and we can take h out of the top line, so we can cancel out the two factors. Now we're left with that monster, and now we sub in h equals 0 to find the limit, so that term and that term can disappear, which is nice. So we're left with 3x squared plus 5. So the derivative of x cubed plus 5x minus 4 is 3x squared plus 5. Example 3. How about you give this one a go yourself first, and then, pause the video, give it a go, and then unpause to see the answers. If f of x equals x squared minus 6x, find f dash x using first principles. So again, put the formula in, then plug in x plus h into the first part, and then minus the same thing over there. So x plus h wherever you see x. So now we expand, it's quadratic, so x squared plus 2xh plus h squared, then expand and minus 6x minus 6h minus x squared minus plus 6x. Now what do? we cancel out what we can. So the x's cancel out and the 6x cancel out, and we're left with that. And then what do? We take the h out so we can cancel out those two factors. Then sub in h. So we sub in h in is 0. So we're left with just the 2x minus 6. Now the values of x where the gradient equals 0. How do we do that? So the value of x for where the gradient equals 0. Gradient equals 0 means the gradient equals 0. We write that out. Now we know what the gradient is. The gradient is 2x minus 6. So we let that equal to 0. And then we just solve to find what x is, which is 3. So when x equals 3, the gradient of the function x squared minus 6x is 0. So this is how you find the gradient. And when you're asked for when the gradient is a certain number, you let that equal to the certain number and find x. Now notice I didn't find the y value because the question is just asking for the x. But if I ask you for the coordinates for when the gradient is 0, then you find the same thing, the x value first, and then you plug it in where? How do you find the y value? Into the original equation. Because if you plugged into this equation, you would find the gradient. Example 4, you try this one and then unpause to see whether you have the same answer. For f of x equals 2x squared plus 4x minus 8, find the gradient of the function where x equals 3. So we have to find the gradient of when x is 3. So this time we let x equals 3 and we're looking for f dash of that. So in other words, f dash 3, what is that equal to? So example 4 is like the opposite to example 3. Example 3, I told you this is the gradient, so you let the gradient equal to that number, find what x is. Now in this question I'm telling you, x is this number, what is the gradient then? So let's find the gradient first. So plug that in using that equation again. So memorize this, you can see how many times we've used this. So x plus h into the first bunch, and then copy down the second bunch with a bracket. Now expand. So here we have a quadratic, x squared plus 2xh plus h squared. Expand that one, plus 4x plus 4h minus 8, and then expand the negative into them. So minus, minus, and then that will be positive over h. And then we cancel out what we can. So the 2x squared, then minus 8 plus 8 cancel out, then the 4x and the 4x cancel out. Now we're left with, take the h out, we have 4x plus 2h plus 4. So we wrote those out, but we took the h out. It's a common factor, so we can cancel it. And now we're looking for the limit of 4x plus 2h plus 4, which is letting h equal 0, 4x plus 4. So that is the gradient. How do we find the gradient at 3? So we plug in 3 into the gradient equation because we're looking for the gradient. So putting 3 into there, 4 times 3 plus 4 is 16. So the gradient when x is 3 is 16. So look for the gradient. Using the gradient equation would give you the gradient. Okay, let's have a look at using the calculator. We're going to use the example here, and we're going to try to get to there using the CAS calculator. So let's type in the equation first. So we have 2x squared, so 2x squared plus 4x minus 8. And our goal is to get to 4x plus 4. So what do we do first? We highlight interactive to find, so our calculator knows that's the equation. And then we need to use this thing here. Where do we find it? It's in math 2. Then we can see that limit is in that corner over there. Now be very careful with this part. Now the h is a variable, so we go to variable h approaches 0. But the f of x, I will just highlight and drop it in. So plus h, plus the h, and then minus, I'm just going to highlight, drop it in. And now I have to do this all over h. So highlight the whole thing, click shift, divide. So now you have a fraction, so you can put h in there. You can write it or you can drag and drop. I like dragging and dropping. So if we hit enter, ta-da, we have 4x plus 4. So recap, go interact, write whatever expression you want, go interactive, click define, so it tells the calculator what it is, then type this out. When you type this out, be very careful that the h is a variable. If you're typing f, f is not a variable, it's in ABC. So h is the variable over here, and f is in ABC. So be very careful with those two things, otherwise your calculator can be confused. But as you can see, the easiest way to do it was to just drag and drop it into the empty spaces. I want to hack the calculator now. So here's the instructions. Again, it just says that be careful with the ABC and the variable. So in summary, differentiation by first principles is this formula here, f dash x, and we call that the derivative. And we say the tangent line to the graph of the function f at the point a f of a is defined to be the line through a f of a with the gradient f dash a. What that says is f dash a is the gradient at a. So differentiating y gives us dy dx, but differentiating f of x gives us f dash x. Thank you for watching, and I'll see you next time. Bye!